So let's get back to composite hypotheses. So with simple hypotheses, we know kind of what to do, but simple hypotheses aren't very sort of natural. Much more natural is something like H0 is that the parameter is equal to something, and then H1, the alternative hypothesis is that the parameter is not equal to that thing. All right, something like this.
So isn't the probability of it being exactly something like really low?
Sorry?
Isn't the probability of a parameter being exactly, like since we're using continuous?
So we're never computing probabilities of parameters being something. We're making assumptions that parameters are in some range.
We're making assumptions they're in some range. Okay.
Yeah, so when I write the probability of C and H0, I do not mean that there's any probability distribution on H0.
You mean probably that
Assuming H0.
Okay.
Okay, so maybe another way of saying this is the probability, assuming that theta 0 is the correct parameter to use in the density function of the critical region. Something like this. Okay? There's a whole range of notations you'll see for people saying this. Okay? So more generally, so this would be a two-sided, two-tailed alternative hypothesis, or maybe you're saying H1 is that theta is less than theta 0. That would be a one-sided, or greater than theta 0. If you're only concerned about one kind of alternative. So these are the kind of alternative hypotheses that you'll see. More generally, I mean, that example we saw, one of the first examples we talked about, where there was a drug, we were going to do 20 samples, and the critical region was whether 14 of them or fewer, 20 coin flips. I forget what the setup was. Let's say it was 20 coin flips, where we wanted to test if this was bigger than something, and the alternative hypothesis is that it's less than something, right? So we had this old example where the hypothesis was theta is less than, the null hypothesis is theta was at least 0.9 for Bernoulli coin flip, and the alternative hypothesis is theta is less than 0.9. So there can be whole ranges of both the null hypothesis and the alternative hypothesis. The parameters can range in whole intervals. And by the way, we're going to talk, to keep things simple, we're going to talk about one-dimensional parameter estimation for at least a while. Maybe we'll get to when we're talking about composite hypotheses. We've already talked about multiple point estimators for multiple parameters. So more generally, a composite null hypothesis will look like theta is in some range, capital theta, 0. So maybe 0.9 to 1 is capital theta of 0. And then an alternative hypothesis will be that theta ranges in, well, capital theta 1, which often might be capital theta 0 complement. The complement taken within whatever space is natural for the parameters. So an example is, you can think theta 0 is equal to 0.9 to 1, and theta 1 is equal to, it's the complement, but it only makes sense for a Bernoulli trial for the probability of a head to be between 0 and 1. So the complement of this in 0, 1 is 0 to 0.9. Yeah, we should definitely have empty intersection. So let's say this one includes 0.9 and this one doesn't. That's an open parenthesis. Ernest.
So is that how you draw your capital thetas? Like you just make a circle with a...
Yes, a capital theta will look like that, and a lowercase theta will look like that. Hopefully you can distinguish the two. I'll try to make them very, like, this one has a little curl to it.
In the book, it's like very explicit.
The capital, well, yeah. Some people will draw like that for a curly theta, for a lowercase theta.
Yeah.
We have to deal with my handwriting. I'm sorry. I'll do my best.
Wait, so that's a lowercase theta.
These are capital thetas. These are trying to be capital. These are rushed capital thetas.
Does those have the little curly?
Yes. Yes. You're right. Okay, I'm trying to make them capital thetas. Hopefully from context it'll be clear what's a parameter, what's a range of parameters, what's a...
Yeah.
Okay? So, so we talked a couple times ago about a power function. So let me remind you what the power function is. Well, the power is 1 minus beta. 1 minus beta is the probability of... So beta is the probability... Let's write this down. Beta is the probability of a type 2 error, which means you're in the complement of the critical region, but H1 was true. So 1 minus beta is that you're in the critical region, and H1 is true. H1 is true. But of course, H1 being true, there's not one value of this probability. There's a range of possible values, depending on how true H1 is, or where in H1 is this parameter theta. So this is really a function. So the power function, usually denoted, or for us will be denoted pi of theta, is equal to 1 minus beta of theta for thetas in the range of the alternative hypothesis. That's literally what the power is. But we can extend it a little bit further to the same thing, the probability of the critical region for all the thetas in general. But once we get the thetas in, bless you, in the null hypothesis, this is no longer beta, it's a type 1 error. Because this is the probability of the critical region, assuming theta is in the null hypothesis. Does that make sense? The point is, in both cases, it's just the probability of the critical region. It's just the size of the critical region with that parameter. But if we're in the null hypothesis, then that is the power, and if we're in the alternative hypothesis, then it's the size. So in this case of n equals 20 Bernoulli trials, and the critical region was that x bar, or nx bar, is at most 14. X bar is the average, nx bar is just the sum of your Bernoulli 0, 1s. If you got fewer than 14 heads, then that was your critical region. And so pi of theta is just the likelihood of this. So it's 20, so it's a sum as k goes from, it's the probability of the critical region. So from 0 to 14, 20 choose k, theta to the k, 1 minus theta to the n minus 20 minus k. And it's this, whether we're talking about the thetas that are in the null hypothesis, and it's this, if we're in the alternative hypothesis or if we're in the null hypothesis. In the alternative hypothesis, the interpretation of this is that it's the size. In the null hypothesis, let me try to speak slower so I point to the same thing that I'm saying. In the null hypothesis, this is the size of the test. In the alternative hypothesis, this is the power of the test. So it's the power function. And we saw what it looks like. Typically, well, there's some, so the place where it switches, so this is the values theta 0. These are the values theta 1. We were testing 0.9. Here's 1 to 0. That's the total domain of parameters. And then the power function as a function of that, so this was theta 1, this range is theta 1, this range is theta 0. And the graph of the power function was something like, well, if theta is equal to 0, the power function looks something like this. So 1 minus beta is, so some people do 1 minus this curve. That's the OC curve that we talked about. So OC curve is 1 minus pi. So some people make the choice to leave beta alone, and then 1 minus alpha would be the opposite direction. So that catches when this is small as opposed to when this is small. Yes, Ernest?
How is the power function continuous when it switches?
Well,
No, I just can't say.
the point is, it's the same as a function of theta. In both cases, it's measuring the probability of the critical region. So all that changes is the values of theta that are in the null hypothesis or in the alternative hypothesis.
Oh, yeah.
But the function in both cases is the probability of the same region, the critical region. So that's why it's the same function, whether you're here or here, just the interpretation of what the function means changes when you switch from a parameter in the alternative hypothesis to being in the null hypothesis.
Are all power functions will look like that?
Well, for our purposes, yes.
Oh,
Okay? But in general, you could have an alternative hypothesis that drastically changes what the distribution is.
yeah.
And then it becomes discontinuous.
Like if it was like a gamma or something.
Yeah, if you could have a null, so for parameter estimation, where we're assuming that there is some shape, and we just don't know what the right parameter is, usually that shape will be continuous as a function of the parameter. So then it will look like this. But there are more subtle applications that we won't get to. Okay? So there's a lot you can read off about the power function. So let's talk about the likelihood ratio statistic. That was the other thing we sort of mumbled quickly last time. So I just want you to know what the power function is. It's a useful thing to have access to. What is the likelihood ratio statistic? And the test is a beautiful theorem here. So remember the likelihood function given the observations x1 through xn, and in terms of the parameter theta, is just the product of the densities, since the xi's are IID, it's just the product of the densities of the observations, assuming you have this theta. That theta is the value of the parameter. And then we talked last time or a couple of times ago about max L0. So this is the maximum value. The maximum value of L, I'll drop the x's if I don't need to speak of the x's, of theta, among all thetas, bless you, in the null hypothesis. We're going to do examples of this in a second. I'm just getting the notation down. So this is the maximum likelihood this is the maximum value of the likelihood function among all thetas consistent with the null hypothesis. And the ratio statistic is the ratio of this to the maximum not in the alternative hypothesis, but over all hypotheses, all theta of L of theta. So by the way, this is the value of L at the maximum likelihood estimator of theta. How do we define this maximum likelihood estimator? We maximize the likelihood. So if you make it as big as possible, then the maximum value is the value at the place where it makes it the biggest possible. Let's do some examples. So what I want to say, I'll define theta 0 hat to be the value at which this maximum is achieved.
Is that unique?
Well, so usually these intervals are closed, and so it exists.
Yeah.
In general, I would need a soup here, and then this might not exist. It might not be in theta 0. There's all kinds of real analysis things that we're going to just avoid. Okay? Let's pretend that there will always be some value for which the maximum is achieved at that value, just so we can speak about these two.
Well, there is one, but there is one that we can choose uniquely.
That's right.
Okay.
Yeah, it might not be unique. If this isn't closed, it might not exist, and so on. But let's avoid all these subtleties. So the likelihood ratio statistic is a random variable lambda. This is a random variable on x1 through xn, and the value that it takes, usually written lowercase lambda. So the lowercase to capital is what is the variable and what is the observation of the variable. I'm writing here little x1, but the variable is capital X1, and it takes values that look like little x1, right? This is a random variable. This is, I got 2. This is a Gaussian normal, standard normal, and the outcome was I saw a 2. What does that mean for me? Okay, so that's what these are functions of the outcomes. This is the random variable. The outcome of that random variable is just the ratio of max L0 of whatever I saw divided by max L of whatever I saw. Remember, the maximum likelihood estimator is itself a function of what was seen. Maybe it's x bar. Well, what you saw determines what x bar is, even though x bar as a random variable is just a random variable. Hopefully I'm not confusing you. Let's do some examples. Let's do some examples, Ernest.
So why is that? Like, why are we doing that? Like,
You'll see in a second. This becomes an important statistic. So it's another quasi-robust, somewhat robust way, actually. It's a rather robust way of constructing critical regions for tests. So Neyman Pearson was one way of trying to construct critical regions that will have certain properties. This will also be critical regions lead to the likelihood ratio test, which will be a nice critical region.
yeah, I just don't know why like you're dividing it like that. But if you're gonna explain it, then
Yes,
Sure.
I'm gonna sketch if I have time. I think I will try to sketch Wilks' theorem, which tells you what the distribution of this random variable is asymptotically. Yes?
Where is theta in the second line?
In the second line, all theta
So the theta that are in the theta not and theta.
and theta 1. Yep, all theta in the domain of thetas. So I'm not taking the ratio.
Taking the ratio of the thetas in the null hypothesis divided by the total.
That's right. So this is not sensitive whatsoever to the alternative hypothesis. Okay? That's right. So this is more worrying about the size, not worrying about making type 2 errors. Errors of type 2. Yeah. Okay. So let's do an example. Here's an example. Here is an example. So I have x1 through xn, IID, Gaussian, known variance, unknown mean, and what I want to do is let's test H0 that the mean is some value mu0 against the alternative that it's not. Okay? Against H1 is that mu is not mu0. So how can we come up with a test for this? Let's look at this ratio statistic. So what is max L0? Here's a test of your understanding of this.
There's only one point.
There's only one point. So theta 0, the range of the parameter mu, theta in our case is mu,
Yeah.
the range of parameter mu is a singleton. There's only one value, so the maximum over that value is just the likelihood. So this is the likelihood of the outcome given mu0 is the mean. In other words, 1 over root 2 pi e, let's make this variance 1. No, let's keep it a variable so you can see what's going on. Minus x minus mu0 squared over 2 sigma squared, and I need a sigma squared down here, times, that was x1, times 1 over root 2 pi sigma squared e to the minus xn minus mu0 squared over 2 sigma squared. Okay, so there's nothing to worry about maximizing this thing, because the maximum happens, so mu 0, well, mu 0 is mu 0 hat. There's only one value in theta hat, so that's the value that maximizes the likelihood in the range of the null hypothesis. What about max L?
X bar.
Yeah, the MLE.
Exactly. The MLE, we already, when we, on the quiz, on the midterm, we computed what the MLE was. So it's, the mu hat is X bar. Right? The maximum likelihood estimator is X bar. So this will be the likelihood with respect to X bar. So it's the same thing. It's this product 1 over root 2 pi sigma squared. There'll be n of them. And then there's an e to the minus x1 minus x bar squared over 2 sigma squared. And, well, it's a sum, but let me write it like this, so I don't do too many steps at once. Can you see that? So the value of this random variable, the ratio of the two, is equal to, the constants cancel out, I get e to the minus, there's a 1 over 2 sigma squared everywhere, and then I'm left with a sum of xi minus mu 0 squared, minus, because these are in the denominator, max L 0 divided by max L, sum xi minus x bar squared. Does everybody see this? So I'm just summing all of these values. I'm dividing by the sum of all of these values. So these are the xi's minus x bar squared. Tahina.
So in the maximum likelihood of the null hypothesis, why is he adding all these terms? Why are we adding all these terms when it just be one, and then should we have like mu dot as one like parameter?
So the likelihood function is the product of, these are all independent. So it's the likelihood of each observation. So we observed x1. What was the likelihood of observing x1 assuming the parameter was mu 0? This is the density function near x1. Same thing with x2 and so on. And they're independent, and so the likelihood function is the product of these observations. Did I answer your question?
Yeah.
Okay. I'm not sure if I understood it, but if you're happy, I'm happy. Other questions? Does this make sense? Let's do a little bit of algebra. Let's simplify this. We've done this a lot of times already, but let's just do it again. This is going to give me xi squared minus 2xi mu 0 plus mu 0 squared. This is going to give me minus xi squared minus negative xi x bar plus x bar squared. I'm just opening this square, xi squared minus 2xi mu 0 plus mu 0 squared, and I'm opening this square, xi squared minus 2xi x bar. Nobody caught me.
Plus mu 0 skull.
Well, it's plus x bar when you open the square, but there was a minus in front that I caught here and here, but not here. Minus x bar squared. Okay? This and this cancel. I get, so let's keep playing with this. How many mu 0 squareds do I get? N mu 0 squareds.
Same with x bar squared.
I get n x bar squareds. And then I have minus 2 xi m0. That's minus 2 m0 times the sum of the xi,
And X bar.
n x bar. So that's that term. And how about here? I get plus 2 x bar times the sum of the xi,
And X bar.
and x bar. Does everybody see that? And we're almost done. Still playing with the exponent. So lambda is equal to e to the minus 1 over 2 sigma squared times. Okay, this is a plus 2n x bar squared. This is a minus 1n x bar squared. So minus 1 and the 2 cancel. This was a minus n x bar squared and a plus 2n x bar squared. So one of these cancels out one of those. And then I have n, so that I have an n everywhere. I have an n everywhere. I have a mu 0 squared minus 2 mu 0 x bar plus x bar squared. That's mu 0 minus x bar squared, which I can write as x bar minus mu 0 squared since it's a square, so changing sign doesn't change the value. There's a reason I want to write it like that. Okay, this is the likelihood ratio statistic. It's a function of the xi, assuming the null hypothesis. Okay, what is the distribution of this? Or rather, let's look at, here's the observation, key observation. Here's the key observation. If I take log of this, log of lambda, and I multiply through by this negative 2, then what I get is x bar minus mu 0 divided by square root of sigma squared over n squared. Let's check this algebra. So I'm taking logs, that gets rid of the e. I'm multiplying through by negative 2, that gets rid of this negative 2. What I'm left with is n over sigma squared times this thing squared. This thing squared is still here. I have a square root of sigma squared squared, that's just the 1 over sigma squared. And this over square root of n squared in the denominator is just a n in the numerator. Again, if that algebra is too slow, please put a star in your notes and come back to it and convince yourself that this really is equal to this. What's the mean of x? What is x bar as a random variable? Normal. What's its mean? Assuming the null hypothesis.
Mu 0.
Mu 0. What's its variance?
Sigma over sigma squared over n.
So this is a random variable, which is a standard Gaussian normal. So its square is a chi-squared with 1 degree of freedom. So this literally is distributed as a chi-squared with 1 degree of freedom. Deep theorem of Wilks there are lots of conditions that we will not talk about. So there are a lot of assumptions that have to happen, but negative 2 log lambda as a random variable converges in distribution to a chi-squared with 1 degree of freedom. Here it's on the nose, a chi-squared with 1 degree of freedom. We didn't need to take a limit. This limit is as n goes to infinity, as the number of observations goes to infinity. I would like to very quickly. The proof is a little advanced. I mean, it's not. It's especially if you allow me to not be precise about what star means, and anytime I do something funky, I throw it into the star, which will keep. I'm not going to quiz you on the proof, but I'd like to give you some flavor as to why this is true, if you allow me. Okay? Or do you not want to know?
I want to know.
There are 2 people that want to know, and the rest of you groan. Oh crap! These 2 people are going to make us talk about some. It's a little bit complicated. All right, let's do this. I'll do it very quickly. For those that don't follow a word that I say, that's okay. We're not going to be quizzed on it. For those that that do follow, great. You can look it up later more precisely. I'll just give you some flavor as to why this is true. So this is very sketchy sketch. Sketchy sketch. 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 All right, the key idea is this. Let's look at max L0. Max L0 is the likelihood of the observation assuming this best thing in the null hypothesis. Thank you. Let's look at log. So I want log of lambda. Lambda is the ratio of these things. So log of L of x at theta 0. Well, L is a product. This is a product, right? F of theta 0 hat of x1 through f of theta hat of xn. So this will be a sum of log of f of theta at theta hat 0 of the observations xi. Now I'm going to do a Taylor series expansion in the variable theta hat 0. So Taylor series in theta hat 0 near theta hat, the true MLE. So what does that mean? Remember, what's a Taylor series? If I have f of theta hat 0, that's f of theta hat plus theta 0 hat minus theta hat 0. I'm just reminding you how to do a Taylor expansion for an arbitrary function. Right? This, I haven't done anything. The theta hats cancel out and I have f of theta hat 0. And this is f at theta hat plus f prime at theta hat times, this is the first order, plus f double prime of theta hat over 2 times the second order plus smaller things. One of the asterisks is the smaller thing really is smaller. Okay, so let's plug that in. This is equal to a sum over I. So I'm doing this in the theta hat variable, so now I get log f theta hat of xi. That's my constant term. Plus. By the way, what is this? The sum of log of the theta hats of the xi is log of the products of the f's, but not at theta hat 0, at theta hat, at the MLE. Oh, this is exactly our log of max L. Right? Hopefully you see that. Let's look at the first order term. So what does it mean to differentiate with respect to, this is the value at one particular point, but I want to take the derivative with respect to theta. So what does that mean? That means d theta of log f theta as a variable in theta, xi, but I want that derivative at theta hat, evaluated at theta equals theta hat, times this linear term. So that's this linear term, the derivative of theta, f theta, with respect to theta, evaluated at theta equals theta hat. That's what it means to take the first derivative at theta hat, times the linear term. And then a second order term. The second order term is, bless you, two derivatives, log f theta of xi, evaluated at theta equals theta hat, times theta hat minus theta squared over 2, plus things that are small. Higher order terms, things that are big O of this difference cubed, which will be a lower order.
So you get like some sort of negative information or something?
Yes, that's exactly what you're getting.
Oh.
Right? And okay, you're getting. Let's take a step back. I'll just keep. Let me go for 2 more minutes on this, and then we come back to general stuff. The key idea I want you to see is happening right here. Right here. what's the derivative of log f theta at the MLE? So if I have a sum, I can bring this sum inside. Maybe that'll help. If I bring the sum inside, this is log of the L.
That's 0.
That's 0.
Because it's a
Because the definition of theta hat is it's the thing where this derivative is 0. Okay? That's the key idea. That's the key thing to see, is that this is 0 because this derivative is exactly vanishing at theta hat. Okay? That's the first thing you have to see. So the ratio that we want, this log lambda, is this thing minus this thing, which we're now down to this quadratic term. And it turns out that this quadratic term is the square of asymptotically a Gaussian standard normal. And a square of a Gaussian standard normal is a chi-square. Now why is that? Because this literally is, as n goes to infinity, the information. Now I'm going to use the law of large numbers. When I average this thing, the average value converges to the expected value of this second order thing, which is literally the Cramer-Rao information, if you recall. So this will converge for large n. Well, I have to divide by n. I have to take the average, and then I have to multiply by n here. This will converge, just use the law of large numbers, to the expected value of this second derivative, log f theta, at theta hat. At theta is equal to theta hat. And by the way, I hope I said here, assume theta then if h0 is true, and h0 is a singleton, then this convergence happens. All right, so this turns out to be 1 over the variance. This is 1 over the variance of theta hat, 1 over the variance of theta hat. So it's an asymptotically best possible in the Cramer-Rao inequality. And so this is its mean, because it's the MLE. If theta hat is, if theta 0 is true, then the average value is, the expected value of MLE is the true mean. So this is a random variable, which is asymptotically Gaussian. Well, when you subtract off its mean and divide by the square root of its variance, and then square, this is a chi-square. All right, so that was a very, very fast and loose, lots of assumptions getting tossed around. I just wanted to point out why there's a chance of this happening. Because the reason there's a chance of this happening is that the definition of theta hat is it makes this first derivative 0. And then this thing just gets added, gets subtracted to the other side, where a difference of logs is a ratio of logs. Is log of the ratio. A difference of logs is log of the ratio. And that's why this thing is a ratio of these maximum likelihoods. For those of you that got something out of that, great. For those of you that didn't, you will never see it again. Just wanted to illustrate some interesting things that are happening. Okay, so back to, so we saw in this very simple case, in the case of literally Gaussian, there's no limit to, we don't have to take n large. This thing is on the nose, a chi-squared with 1 degree freedom. And you can imagine how that'll be useful in testing the value of this ratio. So let's go straight to the test. So what is the likelihood ratio test? Likelihood ratio test. It's just a critical region. The critical region will be the likelihood. Remember, what's the likelihood ratio? Let me put it again here. This random variable is the maximum of the likelihoods, assuming theta is in H0, divided by the maximum over all possible values of theta. As a random variable, what values does this random variable take? What's the smallest it can ever get? 0. So this random variable could be 0 if the likelihood in the numerator is 0. And it can't be bigger than 1 because this is just a maximum of a larger domain than this maximum. So this is an upper bound for this, so this ratio is bounded by 1. So what you're going to do to create a ratio, likelihood ratio test is catch how much less than 1 is this. The closer to 1 this is, well, that means that theta that you observed is within the realm of the null hypothesis, so you can't reject the null hypothesis. The closer this is to 0, the more unlikely the event is. And so if you assume the null hypothesis is true and you find a very unlikely event, your assumption that the null hypothesis is true should be rejected. That's a critical region. Okay? Let's just see what it is in our case here. What critical region does that give us here? So in our example of this Gaussian, so lambda was e to the minus n over 2 sigma squared times x bar minus mu 0 squared. And I want to catch when is this less than k. So I'm going to rewrite the critical region. Well, this is algebra. You'll see immediately that it's that x bar minus mu 0 is at least some other constant. This will be the critical region. So it makes sense from this point of view that if you're trying to catch are you near mu 0, well, what should you do? You should say if I deviate from mu 0 by more than something, that's a place where I should reject mu 0 as the mean. Hopefully you see that there's a tiny bit of algebra that I'll let you do at home for why that's the inequality. The bigger this gets, the smaller this gets, and then I want to catch when it's small. So the fact that the inequalities flip, or take logs of both sides, but then I have to multiply by a minus sign, that flips the inequality. And k is some function of little k. All right? Any questions? Ernest?
Is there a sum in the lambda originally? Or no? Was there a sum?
In the lambda originally there was a sum which turned into x bar. Originally in lambda there was a sum. Right? Lambda was the product of all these likelihoods, which is a sum of a bunch of things. And all those things canceled out except for things that we could write in terms of x bar.
So you took out the n.
We took out the n's, and we were left with this. Ah, that's the problem. I'm pointing to something you can't see. We're left with that. That's what I put in for, I just rewrote that here. I'm trying to catch this condition. That's what it turns out. All right. We have 5 minutes left. I just want to start talking about p-values. We had been talking about confidence intervals. When we make a confidence interval, we're specifying the level of significance first. And why should we choose a p-value? Why should we choose a confidence of 95% versus 99% versus 94% or something? Like why we're making some arbitrary choices. So when we choose to construct confidence intervals, we make an arbitrary choice of the size, alpha, or the confidence, 1 minus alpha times 100%, right? Why 95% versus 99%, etc. In other words, alpha is 0.05 or 0.01. So instead of choosing confidence intervals, the p-value, it's a definition, the p-value of a test is the smallest alpha for which we reject the null hypothesis. So the least, is that how I want to say it? It's the, it's the least alpha for which the null hypothesis is rejected. let me give you an example. Okay. Let me give you a very quick example. So here's an example. You got a bakery. Bakery makes 8-ounce cookie packages of cookies. I don't know why people prefer to think in real terms instead of just abstractly telling me what's going on, but they do, so I'll go with it. From experience will tell you that the standard deviation, standard deviation, not the variance, the standard deviation, sigma, is 16 ounces, 16 hundredths of an ounce. Okay? And you want to test, how's the factory doing today? How are things going? So you pull 25 packages off the line, and you weigh them, and the average weight comes out to 8.091. And the question is, well, it's a little high. How high is it? Is it something we should be concerned about, and should we go back to the processing and the machinery and see what's going on, or is this completely within the realm of? So let's test H0. H0 is that mu equals mu0, which is 8, against, well, what should our alternative be against H1, the alternative hypothesis? So if the weight is too high, if we only want to test mu is greater than mu0, if it's too high, then we're charging some amount, but we're giving the customer more than, we're going to lose money. Right? Well, you don't want to give the customer more cookie than they paid for. If it's too low, some customers will notice and will complain, and we don't want that either. So let's actually test both sides. So this is a two-sided test. We don't want to be too high, nor do we want to be too low. And the question is, what's the p-value? Let's say we're going to test the level, we're going to test it for significance, level of significance, I don't know, 0.01. So in a sense, you can say to yourself, I'll treat 0.01 as significant and anything less than that as insignificant. So what should we do? Well, let's assume everything's Gaussian. So I have my observed x bar minus, so on assuming H0, I have my x bar minus mu0 over square root of sigma squared over n will be a standard Gaussian normal. So this is a z random variable. And what this, when we plug in the numbers, this will be the value of z. So this is the z value. X bar we observed was 8.091. Mu0 that we're assuming in the null hypothesis is 8. We divide by square root of sigma squared, which is 0.16. How many observations were there? Square root of 25. This number comes out to 2.84. And that's supposed to be a standard Gaussian normal. So here's my standard Gaussian normal distribution. I saw not one standard deviation, not two standard deviations, but 2.84, right? Standard deviation is 1. I saw 2.8. This is the z value that I saw. So the least alpha, for which we would still reject the null hypothesis, is exactly the alpha of this tail. But actually, we're taking a two-tailed test. We want to capture both possibilities. And so what is the probability here plus the probability here? Well, the probability here, this amount, is the cumulative distribution at negative 2.84. And then this is twice that. So that's the p-value. The p-value, I'm rushing this, and we're going to, because I'm out of time. We'll do this again next class. But the p-value is exactly this, which now you do numerically, and you see 0.0045. And that is a very low p-value compared to the significance you wanted, which is 0.01. something is wrong. Something is wrong. You should not have gotten this much variation from the mean from the 25 samples that you took. You got to go back to the production line and figure out what's going wrong. All right, we will reconvene on Tuesday with more discussions of p-values.